Fetching a collection of records often hides a performance trap where your application issues one query for the primary list and hundreds more for related details. This computational pattern creates a linear growth in database round trips relative to the number of records retrieved, technically known as the N+1 problem. When code iterates over a parent collection to access a child property, the execution environment triggers a new structured query language request inside every single loop cycle. Each individual query incurs network latency and database overhead. While a single request takes milliseconds, 1,000 requests can stall an application for several seconds. Most object relational mappers utilize lazy loading by default, meaning related data remains unfetched until the specific property is accessed by the application logic. Detection starts by enabling structured query language logging in the development environment to observe the stream of statements issued during a single request. Look for a high volume of select statements targeting the same table with different primary keys, immediately following a broad query on a parent table.
Use database profiling tools to track the total time spent in the database versus application processing. High wait times on simple queries indicate round-trip bottlenecks. Eager loading solves this by instructing the database to fetch parent and child records simultaneously using a single joined request or a combined result set. In frameworks like Hibernate, the join fetch keyword forces the persistence provider to initialize the association in the same select statement used for the root entity. Entity framework users apply the include method on an iQueryable to specify which navigation properties should be populated as part of the initial database round trip. For foreign key or one-to-one relationships in Django, the select related method performs a structured query language join to pull data in one go. Many-to-many or many-to-one relationships require the prefetch related method, which executes a separate query for all related objects and performs the join in Python memory. In the Laravel ecosystem, the with method allows developers to specify multiple relationships to be eager-loaded, preventing the eloquent mapper from looping queries later.
Using multiple joins for different collection associations can lead to a Cartesian product, where the database returns a massive, redundant result set that exhausts memory. Monitor the number of rows returned by a single eager loading query. If the row count equals the product of all collection sizes, you have a Cartesian explosion. Instead of one massive join, execute a few targeted queries. Fetch the parents first, then fetch all related children using the parent identifiers in a single filter. Subselect fetching tells the engine to retrieve collections by repeating the original filter criteria in a nested query, fetching all children for all previously matched parents. Setting a global batch size allows the persistence layer to fetch related records in chunks. If the batch size is 50, 1,000 records require only 20 queries. In Java persistence, applying the batch size annotation to a collection property optimizes loading by using a structured query language in clause for a specified number of IDs. Querying for specific fields via data transfer objects instead of full entities often bypasses lazy loading proxies, forcing the developer to define exactly what is needed up front.
Marking transactions as read-only or using no-tracking queries reduces internal state management overhead, allowing the database driver to stream results more efficiently without proxy generation. Performance degrades exponentially as you eager load deeply nested levels. Limit eager fetching to the first two levels and use targeted queries for deeper leaf nodes. Calling count or sum on a relationship inside a loop is a common source of N+1. These should be fetched using group by clauses in the primary query. Modern databases allow the use of window functions to calculate totals or rankings across related records without requiring separate queries or complex application-side grouping logic. GraphQL interfaces are highly susceptible to N+1 because each field resolver executes independently. Without coordination, fetching a list of items results in redundant resolver calls. The DataLoader pattern solves GraphQL inefficiencies by batching and memoizing requests within a single execution tick, collapsing multiple individual loads into one single database call. Combining eager loading with pagination requires care. Some mappers pull all records into memory to perform pagination if the structured query language becomes too complex with joins. To paginate safely, fetch a page of primary keys first. Then, perform a second query to fetch all required eager associations for only those specific identifiers. Prevent regression by writing unit tests that use custom database interceptors to assert that the number of queries executed does not exceed a predefined threshold. Interceptors hook into the database driver. They count every statement generated during a thread's execution, allowing for real-time monitoring of query efficiency during integration testing. Static analysis tools can scan your source code for common patterns like accessing navigation properties inside loops, flagging potential performance issues before they reach production. In production, use distributed tracing to visualize the lifespan of a request. A long sequence of identical, short-lived database spans is a definitive indicator of N+1. Network sniffing tools can capture database traffic directly. Analyzing the packet stream reveals if the application is communicating too chatty with the database server. Even if the database execution time is 0.1 milliseconds, the overhead of context switching and protocol handshakes makes repeated small queries vastly slower than one large join.
Level 2 caching can hide N+1 problems by serving data from memory, but it consumes significant application resources and still requires the mapper to check for cache hits repeatedly. When you switch to eager loading, ensure that the foreign key columns on the child tables are properly indexed. Without indexes, your single large join will trigger slow full table scans. In microservice architectures, this problem is amplified by network calls between services. One request to an aggregator might trigger N requests to a downstream inventory service. To solve cross-service N+1, design application programming interfaces that accept arrays of identifiers. This allows the provider service to execute a single optimized database query for the entire batch. Identify legacy loops by searching for repository calls within service layer iterations. Refactor these by moving the collection retrieval logic into a single repository method that uses join logic. By only loading the required identifiers and specific fields, you reduce the memory footprint and structured query language execution time, which is especially effective when dealing with large text fields.
Always verify your fix by examining the execution plan. An index seek is preferable to a scan, and nested loops should be scrutinized when the inner table is large. Establish a performance budget for every endpoint. If a code change increases the query count for a standard request, the continuous integration pipeline should automatically reject the commit. Hidden loops often exist in user interface templates. Accessing a relationship property during the rendering of a list will trigger queries outside of your service layer's visible logic. To eliminate the N+1 query, first profile to confirm the issue, then apply eager loading or batching, and finally verify with query counting tests.